Okay, David Green here again. For those who'd like to know a little bit more about the workings of TSG, and it is relevant to the project, I was just going to show you a couple of tricks. Now, firstly, we have is the unmixing done? I'd like to address the nuts and bolts of unmixing. So if I click on a sample here and look at a floater screen, which I'll configure using this T button here, that shows me the thermal spectra. And if I want to see the shortwave spectra, I can use this PA button, which is primary associated. We're in the primary data set here, because that's the one I opened, the thermal one. Now I can put this into a mode by right-clicking on it. TSA, for some reason that doesn't like that. I'll just go to another one. Okay, so here I am in T, right-click, constrained least squares. Constrained least squares is the method that we use in the thermal infrared to do the unmixing. Constrained least squares, so here we go. We have a spectrum and a list of library spectra, okay, that we can use. So we have some background spectra, so thermal things. Garnet is turned on here. Andradite, Grossular. I've clicked on from domain maybe to make sure it's come back to that. So this is where we turn minerals on and off to model the spectrum. So for instance, here I am with garnet. If I turn Uvarovite on, it may or may not use it. It looks like it isn't. I can turn on other garnets, isn't going to use those. So I'm struggling to find minerals I would turn on that would model this spectrum any better than it is at the moment. There we go. If I turn silica on, it's going to put a little bit of opal in there, but only 5%. So that's hardly worth turning it on. So turning minerals on and off is how we model the spectrum. The trick is that we want to have as few minerals turned on as possible. So in the thermal infrared, what we do is we start with nothing, and we turn on only the library minerals that are needed. And there are a lot of tools in TSG that help us do this, right, as a spectral geologist. One of the main ones is the domain editor. So I've clicked something right at the top here. So we split up the drill hole into a whole lot of domains. Here they are, all the way down the drill hole, or in this case, a data set. There are 26 domains here, just as there are 26 samples in the data set. So each of the samples has been treated independently. I can click on this top one. I can edit the active mineral classes, select the thermal infrared, and these are the minerals which have been turned on for this domain. On the right-hand side, these are only the minerals that are turned on in playing with the spectrum. To ensure it's been from the domain, I click from domain at the bottom. Okay, so now this list here on the right will be the same as the list on the left, but the list on the right is for playing with. Now then, notice that in this list on the left, the active mineral classes, we've only got andradite turned on, not grossular. So now, it's philosophically, it's a good thing to do to turn on all the minerals that in each subclass. For instance, in the plagioclases, it would be useful to turn on both oligoclase and andesine because they are difficult to distinguish spectrally, and that's useful to know what both of them would be. But for instance, the almandine garnets are quite different, and so they're in another sort of supergroup or subgroup of minerals. So we really should turn all of these on. So I'm going to turn on grossular, but I will not turn on Uvarovite in this case because it's kind of a weird garnet, and I'm not really expecting it. I could turn it on, but we'll keep it, but it would have to be investigated. And as I said, we have tools for doing this. But in general, we like to turn on all the minerals that are within a subset, like a subgroup like this. So I can go to the next domain and turn on grossular. The next domain doesn't have any grossular or garnet. Next domain has no garnet. This one is no. So I've gone down and done this for all of the domains, and that's what you should do too, actually, because some of them are turned off, and we want to make sure that we are giving the unmixing the options which are available. Okay, so the philosophy in the thermal infrared is start with nothing and build up the minerals we need one by one. The starting set of minerals we use are the ones that are indicated by the shortwave infrared analysis. So shortwave infrared said we've got white mica and chlorite. Well, we better turn those on in the thermal infrared as well, unless we've got a good reason not to. And we build it up from there. A lot of rocks have quartz in, and there are spectral features that we know and love. For instance, this one here is a carbonate. So on the basis of seeing the spectrum, I would attempt to be turning on carbonate for this domain. And this is the way it's done. In the shortwave infrared, things are done a little differently. Let's change this now to the associated data set. And here we have the floater showing a spectrum. I'm going to put it in this T mode again. And I want, with the right click, to use not constrained least squares, that's one we use for thermal, but multiple result overlay mode. There it is. This gives us the candidate unmixing solutions for this spectrum. The spectrum is in white and the model is in brown. That's the calcite plus epidote. The little star indicates the one that's actually been chosen by the spectral assistant as being the best fit. And the difference between the brown curve and the unknown, or the white curve, is summarized in this bracket here, 225. So we want a low number in there. Okay. So and there are a few other little rules to go with this. You don't always get the lowest number, but we can see what other things are being entertained by the spectral analyst in unmixing this. So we've got calcite plus epidote was potentially there, calcite plus epidote plus phlogopite, but it's settled on calcite plus phlogopite as being the best of all worlds. But you can see that the numbers here are pretty close together, so it can be borderline. So this is the automatic unmixing. How is this library of minerals decided? Unlike the thermal infrared, the TSA, the spectral assistant, likes to have all the minerals turned on to begin with. That's its strength. You turn on 150 different minerals, and it's smart enough to only pick the relevant ones that will best model your data set. It's pretty clever. It's got, for each mineral, it's got something like 10 different spectra, so it knows about the range of spectra that are associated with each mineral. And so it takes that into account when it's unmixing. It's mighty clever. And the way we go to adjust that data set, we can do it for the whole hole rather than in domains. We can do it in domains, but it's a bit tricky. But for the whole hole, we go to File, Settings, TSA, and I'll select the shortwave infrared, and I can make mixes of 1 or 2, 3, or 4. I'll go for 3 minerals. And the minimum is going to be 15%. 15%, by the way, is kind of the minimum amount or weight of a mineral that we think we can believe when we use high logger spectra. And we select the active minerals right here in a list, and it looks very similar to the one we just saw. So I'm in the shortwave infrared, and see all the minerals are turned on, almost. There's a couple of furphies like sodium amphibole that are turned off by default, but you can turn them on, and a few weird ones like dolomite, not very common. And we also have lots of things which aren't minerals in here as well, useful for masking up things which aren't minerals. So I can select which minerals are on and off here, and the idea is to leave all the minerals turned on unless you are really sure that a mineral should not occur, and it actually is being picked with the automatic algorithm, and we have to turn it off. Okay, so I can do that, and I could proceed, which I won't. I'll cancel and run it, and it would redo the unmixing. So that's spectral unmixing in the shortwave infrared and spectral unmixing in the thermal infrared. So you really should go through and check these domains and make sure that Andradite and Grossular are turned on all the way through. And we did the update, and we can redo the CLS, the calculation. I can't remember if we actually did that. Here we go. I can get rid of that. I can get rid of that. So now, when I did the set showing just garnet, it's actually recolored it according to the default color scheme. Right click, ox color scaler, mineral colors. Modern is where it's set at the moment, and they're different shades of purple in this case for the garnet group, but we want them to stand out more than that, so I'll go to alternate, and now they stand out. And we can see we now have a few more spectra of andradite and grossular because I've allowed grossular into a few more of the unmixing domains. Now I think that's all I really wanted to show you. You can stop here if you like, but I will just do a quick calculation to parallel another way of working out the composition of a mineral might be to look at the weights of the unmixing minerals which the CLS algorithm wants to put into it. So this sample here, kind of 50-50 grossular and andradite. Okay, so if there is indeed one mineral and the mix we see here is just a modeling artifact to try and model something which is actually in solid solution somewhere between andradite and grossular, then I can use the proportions of the mixing weights to estimate what the composition of the mineral is. This is very helpful when you're really unsure about what spectral feature to use, or you've got too many spectral features, if you've got confounding minerals that are upsetting the apple cart. And there's another case I would use it, is when we have maybe major features just getting in the way. Okay, so I'll do that now. Let's just go to, I'm going to make a scalar. So that the aim here is to build a scalar that shows me the proportion of andradite divided by andradite plus grossular. Okay? And I'm hoping that that proportion will look somewhat similar to the garnet wavelength, which is aiming to track the same thing. Right? So edit, new scalar. I'm going to call it andradite weight. I'm going to put it in garnets, and it's a class extraction. Next, so I'm going to extract it from the unmixing groups, and I don't want quartz, I want andradite, and I'm going to extract the weight. Finish. That one's done. Edit, new scalar. I'm going to do the same for grossular. Okay, and put it in the same place, and it's a class extraction, of course. We grab it from minerals, grossular, we're going to get the weight, and it's done. Okay, now I want to do some mathematics on those. So new scalar, and we're going to call this andradite plus grossular, which will be the denominator in the thing I want to work out. Now I'm going to put this in intermediate, and it's a bit of arithmetic. So I'm just going to add two things together. We're going to find them. Mineralogy, garnets, andradite weight, plus mineralogy, garnets, grossular weight. Done. Finish. And finally, edit, new scalar, we do the division. So now we're getting andradite divided by andradite plus grossular. There we go. And this one I will put in mineralogy under garnets as well. It's another piece of arithmetic, simple arithmetic. We take the andradite weight I had before, and we divide it by the sum of the two, which I had in intermediate, andradite plus grossular. Finish. Okay, now I can plot that up. Let's go to a third plot. So we have the same x-axis. So instead of garnet 1200 wavelength, I'm going to plot this thing I've just calculated, the proportions of the end members as worked out by the spectral unmixing algorithm. Here we go. So there is a lot of similarities there, as I'd expect. The sample that has the mixed grossular andradite is one of the lower ones here. So, and I can export this scalar in the same way as I could export the 1200 wavelength scalar and see how either of them perform for estimating the composition of the garnet. So there's a couple of extra little things that may or may not be interesting or useful, but I thought I'd let you in on a couple of secrets there. Thanks for listening.